This is a quick tutorial on logistic regression, which is regression for binary categorical dependent variables. So as I mentioned in class, there are other extensions to this kind of logistic regression is more a family of techniques than a specific technique, but the one that we've looked at in the course is for dependent variables that have binary or two categories. So we're looking at two category variables. And the example that I want to show you is a model where we predict vote, so whether or not someone votes or is likely to vote, from a set of independent variables, whether they've contacted a politician, the amount of time they spend consuming news media, and their level of education or education in years. So the first thing we want to take a look at is the dependent variable. As I said, it's very important with logistic regression. You remember that these are for two category variables, two category dependent variables. And with Stata, it's a little bit easier if you can get those into the format of 0 and 1, 0 for no, 1 for yes. So a code of 0 if they didn't do the activity, and a code of 1 if they did do the activity or hold the value or performed whatever act and so on. So 1 for yes and 0 for no. And if we look at our variable vote, first of all, there's two ways to look at the categories of this variable. We could do tab, we could do label list, or we could do FRE. Since tab alone won't show us the category codes, we can use either one of these. They'll both give you kind of the same thing. They'll give you the list of values. And we see here we have in this variable three categories: 1 for yes, 2 for no, and 3 not eligible to vote. So the question is whether or not you voted in the last national election. And there's a few missing ones that are already encoded here, so we don't need to worry about those. What we do need to take care of is the coding. First of all, we need to make sure that this is a two category variable, not a three category, and that a 0 is assigned to the no's and a 1 is assigned to the yeses. So in this case, what we're going to do is recode the 3's, those not eligible, and those who said no. We're going to recode those into the 0 category, the no category, and we're going to leave the 1's as they are. So if we take the variable vote, we can use this little piece of code here to change the codes. This is why the FRE command is important, because it lets us know what numbers are attached to each of these different labels. And we're going to recode vote, and in the brackets we're going to specify what the new values are going to be. So 1 equals 1. 1 is going to stay the same because in the new variable we still want 1 to be equal to mean yes. 2 is going to become no, but instead of this code of 2 we're going to use a code of 0, and the 3's are also going to be coded no, so that's going to get a code of 0 as well. Then after the comma we're going to ask Stata not to overwrite this variable, because we might want to come back and look at the more detailed version. We're going to ask it to generate a new variable called vote2. And if we do this and you scroll down to the very end of your variables list, you'll see here that there is a new variable vote with recode of vote2, which is by default labeled as recode of vote. Now if we look at vote2, you'll see that we have 0 and 1, but we don't have any value labels. So the next thing we can do is create a value label system for this. We're going to define, first of all, define a label. We're going to call it yes, no. So the labeling scheme that's going to be stored in memory is going to be called yes, no. In case we need to assign a 0, 1 to any other variables, we can recall this coding scheme rather than redoing this command every time. We're going to give a 0 for no, so between the inverted commas goes the text, 0 for no, 1 for yes. And in the next line, we're going to assign the values of the yes, no system to this variable vote2. If we run all these together, and you see if you're not getting any red text here, any error text, you're probably okay. And now if we go back to inspect our vote2 variable, you see that we have a 0 for no and a 1 for yes. That means now that we can use this new binary variable in our logistic regression, because remember, it's one of the assumptions of this technique, requirements of this technique, is that our dependent variable has two categories. So we're going to look at this in the same format we did as before, where we have our base command, our regression command, in this case logit, our dependent variable, and as with OLS, it's very important that the dependent variable comes first in the command line. So our dependent variable is vote2. Our independent variables then are going to be whether the respondent contacted a politician, their marital status, and their education in years. And then after the comma we've got OR, because we want our coefficients to be in odds ratios rather than in probabilities. So the way that we looked at interpreting and reporting logistic regression coefficients was by requesting odds ratios and reporting them as such. Now we encounter the same issue that we encountered with OLS, which is that unless we include a number of prefixes before our categorical variables, Stata will not recognize them by default as being categorical. So we have a couple here. We've got contacted a politician, marital status and education in years. Contacted a politician is categorical, marital is categorical, and EDU-YRS, education in years, is a ratio variable, a scale variable. We can see what the codes are attached to each of these by running the FRE command. If we return a table for this one, we see we have yes, no. So yes, they did contact a politician, no, they didn't. And in the marital one, it's the same as in the previous example. We have marital status, which is 6 categories. So legally married all the way up to none of these. So it's important that we include the I dot prefix to let Stata know that these are categorical variables. For binary ones, we can also include it because it just makes the labeling in the output a little bit easier to interpret and make sure that we've got the right variable names assigned. So our logistic regression model is going to be of vote2, our dependent variable, the one we created down here by recoding. Contacted a politician with the I dot prefix, marital with the I dot prefix, and education in years does not get the I dot prefix because it is already a scale variable. If we run all of this together now, similar to in the OLS example, we get a table, but now we get different effects for each separate category. As before, we interpret these effects as the effect of being in one category relative to a base category, which by default, unless we tell it otherwise, is category 1. So this is the effect on the odds of voting for those in a legally registered civil union relative to those legally married. This is the odds ratio for those divorced relative to those legally married, and the ratio for those widowed relative to those legally married. So these odds ratios are comparing this category against the first one, each category compared to the legally married category. In this one, the CONTPLT one, we see here we have category 1 is yes, category 2 is no. So what this is telling us is that the odds ratios for those in the no group are 0.46 relative to those in the yes group. If you want to look at in some more detail about how to interpret these, there is a separate video on the calculation and interpretation of odds ratios that's also up on the YouTube playlist that I encourage you to look at. The first thing to look at is whether the odds ratios fall above or below 1. This is kind of like reading it as a positive or negative effect. If the odds ratios are above 1, then the outcome is more likely for this group relative to the base group. If the odds ratio is below 1, then it's less likely for the reference group. So in this group, we could say the odds are 1.5. If we're rounding, we would say 1.6 times those in the widowed group relative to those in the married group. So they're 1.6 times more likely to have voted. The ratio of odds to those widowed relative to those married is 1.56. In education, we can follow the same additive effects interpretation. What's the contribution of each additional year of education to your likelihood of voting? And this is relatively close to 1. It's a very small effect. It's somewhat negative, so this would imply that with each additional year of education, the odds go down, controlling for marital status and political engagement. And finally, we also want to check for those that are statistically significant, that we're reasonably sure are non-zero in the population. And the significant categories in marital status then are this one for civil partners, those who are divorced, those who are in a legally registered, or sorry, none, those in the none category. And this one is also statistically significant, as are the contacted a politician group. As with OLS, we also get a, not an adjusted R squared, but a pseudo R squared. So it kind of approximates the R squared that we saw in the OLS context, and we can read it and interpret it the same way. 0.078, or we could say we're explaining about 7% of the variation. And we also get a likelihood ratio test for the model itself, for the fully specified model, and we want to check and see if this falls below 0.05 as well. In this case it does. And we also get a few other bits of information like our number of observations and so on. And over here, as with the OLS example, you also get confidence intervals for the odds ratios. So those are the key pieces of information to look out for in your reporting, and that's just a quick tutorial on how to conduct logistic regression in Stata.